All right, so the next 3 lessons, 2 of them we're going to do this week, 1 of them we won't get to until after midterm, is going to be all about sine and cosine and taking a look at what it looks like when you graph them. Does anybody know, either maybe I have shown it before or just from another class, does anybody know what these 2 graphs look like? They look very similar, but they're definitely not straight lines or like parabolas. It's a very different kind of graph than what we've studied.
They're like waves.
Yeah, they look like a wave. So we don't do a ton of graphing on the calculator. Most of the graphing for sine and cosine we do is going to be by hand. But just to kind of show you what they look like. Okay, that's the graph of, that one's sine. And the one you're going to see in red in a minute is cosine. Okay, so they look very similar. Okay, what do you notice about looking at those 2 graphs? Anybody notice anything about them? Yeah?
They seem to be horizontal shifts of each other.
Yeah, sine and cosine are horizontal shifts of each other. They are a shift of each other by a certain amount of degrees or radians. I'll give you a hint. Each tick mark on the x-axis there is not 1 unit. So they're not shifts of each other by 1 unit. They're shifts of each other by 1 tick mark. But does anybody know or have a guess how much each tick mark is in degrees on the x-axis? Yeah.
Pi?
No, not pi.
2 pi?
No, not 2 pi. Yeah?
Half pi.
Half of pi, yeah, or 90 degrees. That's exactly what sine and cosine are. So if I were to take the red one and shift it 90 degrees to the right, it would be right on top of the blue one. Yeah. So they are horizontal shifts. Does anybody notice anything else? Anything else about those 2 graphs? Yeah?
Cosine hits the y-axis at the peak of the wave, whereas sine hits it right between the peak and the trough.
Yeah, so they do hit their maximums and minimums at slightly different points because they are shifted from each other. Yep. How about in terms of how high and low they go? Yeah.
They only seem to go to positive and negative half pi.
So the units on the y-axis do go by 1s.
Okay.
Yeah. So the units on the y-axis go by 1s. On the x-axis, it goes by 90s, or if you're in radians, pi over 2s. But yeah, they go up to 1 and down to -1. How about when you're drawing it? We've talked about this property before. When you are drawing sine and cosine, what happens as you trace it? Or what don't you have to do as you trace this graph from the beginning to the end? This is an important property of sine and cosine. Yeah?
It's, you don't have to pick up your pencil.
You don't have to pick up your pencil, yes. Does anybody remember what that's called?
Continuous.
Continuous, yeah. Sine and cosine are the only, out of the 6 trig functions we've studied so far, they're the only ones that are continuous. Okay? Every other function, you would have to lift your pencil to draw. Yep. So that means the domain of sine and cosine are all real numbers, because they are continuous. And there's, yeah.
What about the range?
Well, the range is between -1 and 1. All real numbers between -1 and 1. Now, you can change that. If you want it to be between like -2 and 2, you could do a vertical stretch by a factor of 2. And then it would stretch the wave out. So the range you can change. The domain you cannot. No matter how you shift or stretch that, it's always going to be all real numbers for the domain of sine and cosine. The other trig functions are very different. Okay, but we don't, that's 6-4. We won't look at that until after the midterms. That's a ways away. So another thing that you can do to kind of see an application of sine and cosine is if you look at, it's called an oscilloscope, and it basically takes the frequencies that it hears and it makes a graph of it. Now, as I'm talking, it doesn't look like a wave, and that's for several reasons. One, my volume is changing. I'm not talking at exactly the same volume, and the frequency of my voice is changing. I'm not using the exact same frequency. But if I make a sound that's the same volume, same frequency, then it would look like a wave. which I can do in a second.
It's actually a bunch of sine and cosine waves in form of the Fourier transform.
Yeah, it's a very, very complicated graph of somebody's voice. That's why you could use voice as a, I don't know if it'd be like, it wouldn't be 100% secure, but you could use a voice as kind of an identification or like in addition to maybe like a password or something, like a voice scan. Because everybody's voice is somewhat unique. I wouldn't say perfect, because if you recorded somebody's voice and that was the only password you had to get into something, then you could just play their voice and it would get you in. But a voice is definitely something that's pretty unique. Yeah?
I was gonna say it's actually just a bunch of transforms, sines and cosines added up into one single wave.
Yeah, yep. So it's a very, very complicated picture of a bunch of frequencies all combined together. But I can make that picture look a lot simpler if I were to just like whistle. So if I go, it's as good as I can do. But you could see the volume will fluctuate a little bit. But you could see the pattern of the wave was much simpler than what you're looking at there. So that's one application for sine and cosine. We can analyze sound frequencies. Other applications you might see, like if you're in physics and you study electromagnetic waves, those are different than sound waves. Electromagnetic is like light, infrared, ultraviolet, microwave, different kind of wave, but you can still model it using the same kind of picture. But we'll look at a few things related to sound waves. Like what happens if you do a phase shift? How does that affect what you hear? Or an amplitude change? Okay. So out of the 4 transformations, shifting left and right, shifting up and down, stretching left and right, stretching up and down, 3 of them I can play as a sound, and you can actually hear what they do. The 4th one, there's no real effect that I know of that correlates with sound. So that one I can't. All right, so let's close that and take a look at a little bit more about sine and cosine. So first of all, sine and cosine are the first 2 functions we've studied this year that are called periodic. The idea of a periodic function is basically that it repeats itself. So once you know what part of the function looks like, you could basically copy and paste that forever, and that would be what the function looks like. All the basic trig functions that we study are periodic. They're not as simple. The other ones aren't as simple as sine and cosine, but they still repeat themselves. And when I talk about repeating, I'm talking about the y values. The y values will repeat themselves after a certain amount of time has gone by. Let me see if I can kind of show you an example. So let's say we had that wave. Generally, when I ask you to sketch a sine and cosine graph, you're only going to sketch one section of it. Okay, that's called a section. Okay, the more proper word is a cycle. That's one cycle of a sine, or it could be a cosine wave. We don't know. But it starts at 0. The highest point it hits is 1. Goes back to 0. The low point is -1. And then it goes back to 0. And you're going to keep seeing that section repeated over and over. 0, 1, 0, -1, 0. Those are the y values that repeat. 0, 1, 0, -1, 0. And I can just keep pasting that section forever. And you're going to keep getting those same y values. The amount of time that it takes to repeat is from that blue line to that blue line. There's a name for that distance. It's the distance that it takes your graph to basically do its thing and then start over. And we'll talk about how big that distance is in a second and what the name of that distance is. Actually, if you look at the calculator, you could probably tell. Can anybody tell what the distance would be? Just focus on this wave in black. From here to there. If you count how many tick marks it is and you know what each tick mark represents, you can figure it out.
2 pi?
It's 2 pi, yep. That is the length of the time that it takes before the graph finishes a cycle and then starts the next one, 2 pi. In radians, or in this case,
360.
it would be 360. When we are graphing on the calculator, there's a new zoom that we're going to use quite a bit when we do trig, and that's zoom 7. If you do zoom 6, a lot of times the graph that you're supposed to have that looks like a wave doesn't look like a wave at all. Okay? That's exactly the same graph you were just looking at. But looking at that, that doesn't look like a wave at all. And the reason it doesn't is because when you do zoom 7, each one of these tick marks is 90. So you're really going from, let's see, like that's negative 90, 180, 273. So that's negative 360 way over here. And that's positive 360 over there. When you do zoom 6, you're going from negative 10 to 10. That's nowhere near enough to see the cycles. Okay? Not in degrees. Okay? You could set it up manually if you want. Like if you do negative 360 to 360, now it'll look a lot better. Okay? It's going to look more like a wave. It's kind of squished because you're still looking at negative 10 to 10 on the y, and the graph only goes negative 1 to 1. So you want to zoom in a little bit more. That's why I usually do zoom 7. Zoom 7 is a good starting point when you're graphing something that has a trig function. Okay, and if you want, I'll put tangent up just so you can see what it looks like. It is periodic, meaning it has a pattern to it and it repeats, but it's a totally different looking graph. First of all, the range is all real numbers, and it has vertical asymptotes every 180 degrees. So that one's a little more complicated. We're not gonna study that one. And secant and cosecant, they're also very different looking than sine and cosine. All right, so the length of that interval between those two blue lines, that is called the period of the function. It's the amount of time it takes before the graph repeats itself. For sine and cosine, if you don't do anything to them, the period is 2 pi. Okay, there's only one transformation that would change the period. That's a horizontal stretch or compression. That's the only thing. If I wanted to do a horizontal stretch or compression, where would I put a number in that function? On the inside of the parentheses or the outside? Which one would cause a horizontal transformation? Yep.
Inside?
Inside. Would I add it to the x or would I multiply it by the x?
You would add it to the end.
No, adding it would cause a horizontal shift.
Oh, you use it. Stretch.
We want to stretch, yeah. So if we want to stretch it or compress it, we would multiply it. What do you think putting a 4 in front, well, not there, that's a vertical stretch. What do you think putting a 4 there would do? Stretch it 4 times as much or compress it 4 times as much? Yeah?
Compress it.
That's going to compress it 4 times as much, which means you're going to get a lot more waves between those blue lines. In fact, you're going to get 4 times as many now. Okay. So by putting a 4 there, we have changed the period length of the graph. It's gotten much shorter. if we wanted to lengthen it, what kind of number do you think I would have to put in front of x? If I wanted to stretch it, make it longer. Anyone else? How about Dex? You have an idea? What kind of number we'd put to lengthen it?
Maybe one like lower than 1.
Lower than 1, yeah. So if you do something like 0.5x and you graph that, now your wave is going to be elongated. And we'll talk about on probably Friday, tomorrow, what that would do to the sound. Okay, that's the most interesting one in terms of what it would sound like when you stretch or compress the wave. I think I used that word already. Cycle and period I'll pretty much use interchangeably. So if I ask you what's the period of the graph, what's the cycle length of the graph, same thing. Cycles, you'll see that used more, especially when you're talking about things with like electronics, electricity. There's a measurement in cycles per second. Does anybody know what you call that? Something that's measured in cycles per second. It's actually named after a person. It begins with an H. Yeah? Hertz, yes. You measure something cycling per second. That's called hertz. So I have, I don't know if it showed it on that oscilloscope I had earlier, but there is a screen I can go to in that shows me the frequency that the oscilloscope is hearing, and it's measured in hertz. A low hertz number would be a low frequency, like 45 hertz. That's about as low of a frequency as I can produce with the speakers and sound equipment I have in here. Higher hertz, like 9,000, 10,000, those would be an extremely high frequency sound. The upper limit being about 20,000, and that's, most people wouldn't be able to hear 20,000 hertz in here. Maybe when you were really little, you could still hear it. But those high-end frequencies, they start to become harder to hear as you get older. So it's kind of neat. You can kind of slide the frequency and see where all of a sudden you lose it. Like some people can hear to like 11 or 12,000s. I think most people in here can probably hear to 17 or 18,000 still. Probably not a ton above that though. Okay, but that's the measurement of cycles per second. It's called hertz. You see it used in electricity. Like if you look at specifically alternating current, it has a cycle of 60 hertz. That's what it needs to run at in the United States. So when you plug something in, it works as expected. Other countries they might use different amounts of hertz, different voltages, things like that. But I'm just focusing on hertz. If you have a generator for your house, it's important that it makes 60 hertz. Okay? If it doesn't, then things won't run right. Okay? If it produces like 58 hertz to 62 hertz, it's probably going to be okay. But if you try to plug in something that's expecting 60 hertz, and you got a generator making like 40 hertz, it's going to be a bad day for that piece of equipment. Maybe a light bulb wouldn't be as affected as much, like an old light bulb, but like sensitive electronics, like a computer, TV, you're going to ruin it if you plug in something that's that far off with the hertz. Okay? Motors wouldn't run right. Sometimes you can even hear it, like if you're used to like what your furnace sounds like when it's running normally, and when you run it on a generator, it might sound just a little bit different, and that could be because the generator is making electricity it's just a little bit off from what you normally have, right? But it's still okay enough to work. So yeah, there's a lot of different places that these measurements are used. Okay, let's graph those two and see what happens. Sine negative x and negative sine x. What kind of transformation is that negative? You put the negative inside, it's a, yep.
I think it's a vertical flip, or is it horizontal?
It's horizontal. Remember, anything inside the parentheses is your horizontal. So that's a horizontal reflection. And then the negative on the right side is a
Vertical.
vertical. Well, if you graph sine and put a negative in front, well, in front of the x, or a negative in front of the whole thing, the graph is going to look exactly the same. If you can put a negative inside or in front and it looks the same, that means your graph has a certain kind of symmetry. That's called symmetry about the origin. But in general, putting a negative on the inside and putting it on the outside is not the same thing. One's a horizontal reflection, one's a vertical reflection. It just happens to be the same result in this particular graph. That does not work with cosine. Okay, so sine is symmetric about the origin. Okay, why is that important? Well, when we start talking about trig identities, if you have a negative inside the parentheses, that makes life very complicated. With sine, we are allowed to take that negative, put it in front, and it still means exactly the same thing, but it's a lot easier to work with if it's not in the parentheses. So that's when we start doing a lot of algebra with this stuff, that's where that becomes important. Well, let's see what happens with cosine. I'm going to try the same thing. I already told you it doesn't work. Okay, I'm going to do the negative on the inside and then the negative in the front. And it's not going to work. But I'm more interested in what will work then. When you do the negative inside and negative in front, you get two different results that are exactly 180 degrees out of phase. So does anyone have an idea of what I could do that would be the same? Yeah?
Make the negative cosine of x positive.
Yeah. If you graph cosine negative x, and you just graph cosine x, okay, watch how those look. They're identical. So putting a negative on the inside of a cosine function has no effect on it at all. And that's because cosine is symmetrical over the y-axis. So this one's even handier than the one above. Negatives inside parentheses are going to make life complicated when we're doing identities much, much later. If there's a negative and it's a cosine, you can just get rid of the negative. It makes no difference at all. And you can see that same idea a little bit simpler if I do cosine of 50 and cosine of negative 50. That negative makes no difference. That's showing it for a specific value. That's showing it for the graph of every value. Any question on that? Okay. All right, so graphing sine and cosine. Kind of already pointed this out a little bit, but you need 5 coordinates. You generally, when you're graphing it, you want to get all the places where it crosses the x-axis, which for a sine function, that's the section that we draw, that's 3 of them, the high and the low. So that gives you a total of 5 coordinates. So if you noticed when I showed you the worksheet for homework, there's a table on the side. It's got 5 spots for 5 coordinates. That's what I'm going to show you how to find right now. Now, if you're picking 5 coordinates from here to here, that breaks your graph into 4 sections. 5 coordinates gives you 4 sections. There's 1, there's 2, there's 3, and then the last one I'll just leave in black. That's 4. Now, we already know from talking about the cycle length, it's 360 degrees broken up into 4 sections. Well, if you break 360 degrees into 4 sections, that makes everything 90 degrees apart. So each one of those points is pi over 2 radians, or 90 degrees apart. Right, and we'll write down what those 5 coordinates are right now. The coordinates that we start with are very important, because every transformation that we do is going to be based on those starting coordinates. So if your starting coordinates are wrong and you shift them, then guess what? Your shifted coordinates are going to be wrong as well. Okay, so we really have to make sure we get these starting coordinates right. And I think I have a table down below. I'm going to put them all in just a second. Okay, so let's start. That is the actual picture of sine. Okay, that is, to scale, that is accurate. So let's go through labeling all 5 of those coordinates. Start with that one. Nick, what's the coordinate of that point?
0, 0.
0, 0, yep. Sine is going to start by going through the origin. Okay, so we got 0, 0. Okay, next coordinate is right there. So let's do that one. So the x value first, and then the y value. Yep.
Pi over 2, 1.
Pi over 2, comma 1. Yep. So that's your second coordinate. Let's go back up, get the third one. How about that coordinate? What's that one? Yeah. Yeah, that's going to be pi comma 0. Okay, that's the third one. All right, let's go to the fourth one. What's that fourth coordinate going to be for sine? Jack, what do you think?
3 pi over 2, comma negative 1.
3 pi over 2, negative 1. Now you're at the lowest point that you're going to be in the cycle. And then the last coordinate, you are now back where you started, 2 pi, comma 0. So those are your 5 coordinates for sine. Now, cosine is all of these coordinates just shifted. So if you just take all the y values in this right column, and if you could just shift them all up one slot and leave all the x's where they are, those would be your new y values. Yeah? Yeah. So take all of those, slide them upright, and that's cosine. So you'd have 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and then 2 pi, you're back where you started. So those are the 5 initial values for cosine. And it does make a difference which one you use. If you use the wrong table, the x's would still match, but all the y values would be off by 1. And when we do a problem involving graphing sine or cosine, most of the points is going to be in making the table. Generally, the way I would do it, if this was a problem on the test that said graph cosine, I would ask you to make this table, and I'd give you 1 point for every number you get right in the table. And then I'd have you draw a sketch, and the sketch is usually worth 2 points. So a graphing problem I generally make worth 12 points. 10 of it comes from the table, 2 of it comes from the picture. So the table is a lot more important than the picture. Okay, everybody have those 2 tables. Okay. All right, so the way that we're going to start out is we're just going to do one transformation at a time. It's a little bit slower than what we're used to doing. Usually we just learn every transformation at the same time. Stretch, shift, reflect all 6 of them together. Today, we're going to do one thing at a time. Because we're only going to do one transformation, that means one column in your table stays the same, one column changes. Okay, so you can always count on one column staying the same and one column changing. That's going to be the same tomorrow as well. When we finish this lesson after midterm, 6.3 part 3, then we're going to combine all the transformations together, which is what we normally do right away anyway, but we're just going through it a little bit slower. Okay, so individual transformations, that's all we're doing today. All right. So everything I've told you so far, that's just kind of general background information about sine and cosine. Now we're going to talk about 2 specific transformations. A phase shift, which is what they call a horizontal shift. I don't know why they call it phase shift with sine and cosine. There's no other graphs that really use that term, but sine, cosine, tangent, all those trig functions do it. So we're going to do shifting left and right, and then we're going to do shifting, I thought it was up and down. Yeah. So today we're going to do the 2 shifts. Tomorrow we'll do the 2 stretches. Okay, so what is a phase shift? Phase shift is a horizontal shift. It's when the graph moves left or right. Now, when I teach trig, when it was its own separate course, this is the first time they've ever seen transformations. So they don't really know how a horizontal shift works. We've studied horizontal shifts with every function we've done all year. So first of all, when you do a horizontal shift, does it involve adding or subtracting a number, or does it involve multiplying? Yeah.
Multiplying and dividing. What if it's a
No,
fraction?
not for a phase shift. Not for a horizontal shift.
Oh, adding.
For shifting, that's always adding or subtracting. Would it be inside or outside the parentheses? Which way is horizontal? Yep.
Inside.
Inside. Positive number is going to move it which way? Like if you had like x plus 90 degrees. Plus is going to move it to the
Left.
left. Yep. And negative moves it to the right. So we already know all that. Okay, so hopefully everything you're writing down now, you should already know. So phase shift, adding or subtracting inside the parentheses. It is the first transformation you would deal with when we start doing multiple. That's why I use the letter A. Just like I have all year. Okay. Minus a number is going to move it to the right. Plus a number is going to move it to the left. So nothing new there at all. When we do shifting left and right with other functions, you can shift by any amount. And you can shift by any amount you want here. But I'll tell you, the common amounts you're going to see is a shift of 90 degrees, 45 degrees, and 180. Could you shift it by 57 degrees? Sure. It's just not a common one. 45, 90, and 180. We see a lot. In radians, that would correspond to 45 is pi over 4, 90 is pi over 2, 180 is pi. All right. So the first thing we have to do when we're sketching a phase shift is we're going to take that table that we had and we're going to modify it to reflect doing a horizontal shift. Which values are not affected by a phase shift? Yep.
The x values,
So which way does a phase shift move the graph?
horizontally.
Moves it horizontally. So if you had a coordinate that was here and then it was here, what changes between those two coordinates, the x or the y?
Wouldn't it be the y? Because,
Those two coordinates would have the same y value.
okay.
They both have, in that case, they have a y value of 0.
The x.
The x is what changes. So when you shift left and right, the x values change, the y values do not. So from your original table, you can copy the y values down. They are not changing. I'm not saying they never change. I'm just saying they don't change when you shift left and right. Now, the x's are going to change. And remember, it's the opposite of what we would expect. So if you have minus pi over 2 in your graph, your points are going to shift which way, first of all? Minus is going to shift to the, yep, to the right. And how much to the right are they going to shift by? Pi over 2. So if I want to take a point and I want to move it that way, pi over 2 units, I need to add a number to all my x values. Okay. So remember, horizontal shift is the opposite of what you would expect. If you see a minus pi over 2, you need to shift everything right by adding pi over 2. If you have a problem that has plus and it has a pi in it, you need to move everything left. Which operation moves things left? Subtraction. Okay, so you always do the opposite of what you see. So let's start with writing down the column we know is not changing, which is the y's. Can someone remind me for sine, what are my first 5 y values? Okay. These are the values that keep repeating. Right? Yep.
0, 1,
0.
0, -1, 0.
So sine is going to look something kind of like that. So starts at 0.
That's 1.
Well, it's
0, 1,
0,
0, -1. That's what he said.
-1,
0.
and 0. So 0, 1, 0, -1, 0. Now, what would my original x values be? I'm going to put those kind of to the left of my table, just so I have them for reference. Yeah, right?
0, pi over 2,
0,
pi, 3 pi over 2, 2 pi.
2 pi. So those are not meant to be in my table. Those are meant to be off to the side. My answers, final answers, are going to go in the table. All right. What am I going to do to all of these original x values to turn them into the new x values? Yep.
I'm just going to add pi over 2.
I'm going to add pi over 2. Okay. And I didn't give you any decimals in the original x values. I do not want any decimals in the final answers. Okay, so we need to find common denominators, add these up. First one, that's usually pretty straightforward. 0 plus pi over 2 is pi over 2.
What?
You're all set. When you see green, you're good.
All right.
Yeah. So pi over 2. The next one, pi over 2 plus pi over 2, already has a common denominator. What's 1 pi over 2 plus 1 pi over 2?
1 pi.
Yeah, 2 pi over 2. Or just pi. Right? How about this one? Let me do it off to the side. Pi plus pi over 2. What's the common denominator going to be between pi and pi over 2? Yeah? No, common denominator is going to be a whole number. It's going to be a whole number. Well, what's the denominator on pi right now? 1. So what's the common denominator between 1 and 2? Common denominator has to be at least 2 or higher in this case. It can't be lower than any of your individual denominators. Yeah,
Is it 2?
it's 2. So to get a common denominator, we're going to multiply by 2. So now what's 2 pi over 2 plus 1 pi over 2? 3 pi over 2. 3 pi over 2. The next one already has a common denominator. What's 3 pi over 2 plus 1 pi over 2? That's 4 pi over 2, which is 2 pi. And eventually, if you start to see the pattern, this is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What do you think the last one is? Yeah? 5 pi over 2. And then it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. That's the pattern. Now, we started with 5 values, and they were all equally spaced. We took every one of those values and we shifted them right by the same amount. Are these new values in red, or new values in black, still all equally spaced? Yeah, because we started with values that were equally spaced. We shifted them all together, so they're still equally spaced. Because these are all equally spaced, that is what I'm going to use to label my axes. These would be awful numbers to try to graph. Right? 1.57, 3.14, 6.28. So don't set up your tick marks to go by one step. The only condition when you set tick marks up is they have to be equally spaced. So let's call this 0. That tick mark will be pi over 2, just like the calculator does it. Pi, 3 pi over 2, 2 pi, and 5 pi over 2. That's how I'm going to number my tick marks. That's going to make graphing very nice. Okay, it's going to make everything land on a nice spot. So pi over 2, 0. That's your first one. The next one is pi up 1. 3 pi over 2, 0. 2 pi, we're at negative 1. And then the last one is 5 pi over 2, and we're at 0. That is your sketch. That's the new one. You do not have to graph the original in this problem. I think in the homework I have you graph it. But the original would look like this. That's just there to show you the shift. Okay. And the point is we only sketch one section. Because if you needed to sketch another section, all you'd have to do is copy and paste what you already have. And that's it. So on a test, 10 points for the table, and then 2 points for the sketch. But all you need to do is sketch the new one. You do not need to sketch the original on the test. Again, in the homework, I think I had you practice the original. Okay. Any questions on that one? So out of the two we're going to do today, this one's harder because of the denominators and the pi's. The x's are always messy to work with because they're all fractions. The y's are very easy to work with. It's just arithmetic with ones and zeros. Okay, so we're doing the harder one first, and then we'll finish with the easy one. Cosine of x plus pi. Okay, which values here are not going to change in my table? Yeah?
0, 1, 0, negative 1, 0.
So which column? X's or Y's?
Why?
Y's are not changing.
You could invert the y's though too.
So what? Can you say those Y's again?
0, 1, 0, negative 1, 0. Right?
Okay, 0, 1, 0, negative 1, 0. Are those the Y's for sine or cosine? That's sine.
Oh.
So what you'd be doing sine of x plus pi. We need to start at a different point with my y's. Yep.
1, 0, -1, 0, 1.
Yes. So you get 5 points just for getting those right. Is half your table. Okay. X's off to the side. Just going to put those for reference. And what are we going to do to all of my original x's to turn them into the x's I need for this graph? Yeah.
Subtract 5.
Right, that's a plus. Everything needs to shift to the left. And all my final answers are going to be in that table. All right. What's 0 minus pi?
Negative pi.
Negative pi. What's pi minus pi?
Minus half pi.
Oh, it's pi take away pi.
But 0.
So yeah, it's just 0. Taking away the same thing from itself. And what's 2 pi take away 1 pi? Pi. Now, if you get those, kind of a trick you can do here is whatever's halfway between them, that's the next values. So sometimes I use a trick like that in my head to figure it out, if I don't want to do the common denominator. But that assumes you got these two right, which we did. What's halfway between 0 and pi?
Half pi.
Half pi. Or, if you did the common denominator, 3 pi over 2, take away 2 pi over 2, would be 1 pi over 2. And what's halfway between negative pi and 0? Yeah,
Negative 5 over 2.
yeah, negative pi over 2. Or, if you don't like that trick of finding what's halfway between, find the common denominator and subtract. But you'll get negative pi over 2. Any questions on the table? Yeah.
On the y-axis, how do you know the numbers?
So those come from the original table that I gave earlier. So
Okay.
there's 2 original tables. That's from the cosine table.
Okay.
That's right there. All right, and now the sketch. Again, we started with 5 x values that were all equally spaced. We took them and shifted them all together, so they are still equally spaced. So use them as your markers for your tick marks. Negative pi over 2. You don't have to label 0. I know the axis is 0, but if you want to, that's fine. Pi over 2 and pi. We're going to have 1, 0, negative 1, 0, 1. So 1, 0, negative 1, 0, 1. Now, you want to be careful when you sketch that, because that's what your graph looks like. Okay? It's a wave. The section of the wave that we're capturing is this, not this. That is not what it looks like. Okay? It's a graph that curves. So we kind of make it so it curves down and back up. In calculus, you'll talk a little bit more about how that curve, or the names of the parts of that curve, but this section is what we call concave up. Concave up means it would hold water, if you want to think of it that way, where this section and this section are concave down, meaning water would fall out of them. So there's a switch in what we call concavity at that point and that point. You don't have to know the details of that. I just want, when you sketch it, I want it to look like it's curved. Okay? Not that. Okay. Any questions on that one? Okay, let's do one more phase shift. A little tricky with the numbers because it's pi over 4. I'm not worried about sketching it because once you get your table, the sketch is easy. Okay, so So which column here is staying the same?
Y,
Y's. And what are my y values going to be?
0, 1, 0, negative 1, 0.
Perfect. Okay, my original x's, hopefully over time you're going to memorize those pretty quick. What are my original x values for sine or cosine? Same thing. Yeah.
0, pi over 2, pi, 3 pi over 2,
2 pi. And now, what am I going to do to every one of them? Yep.
Subtract pi over 4.
Right, they all have to move to the left by pi over 4. So I usually just do the first couple, and once I see the pattern, I can just continue that. I don't have to keep finding common denominators. Okay, so there's the first one. 0 minus pi over 4, it ends up at negative pi over 4. How about common denominator between 2 and 4? Remember, common denominator cannot be smaller than any of your individual denominators. Yep.
4.
4. So we're going to do times 2 and times 2. What's 2 pi over 4? Take away 1 pi over 4. Yeah? Pi? Just pi? What about your denominator?
You just change the 2 pi to be 2 pi over, oh, never mind, 3 pi.
So it's going to be what?
3 pi.
So 2 pi over 4, take away 1 pi over 4. Did all that work to get that denominator, so that needs to stay there.
Oh.
1 pi over
1 pi over 4. Let's do another one of those. So pi minus pi over 4. Okay. What's the common denominator between 1 and 4? Yeah? 4. So let's do a times 4. And what's 4 pi over 4? Take away 1 pi over 4.
3 pi.
3 pi over 4. And now you should start to see a pattern that you could follow. Negative 1 pi over 4, 1 pi over 4, 3 pi over 4. What do you think the next one is? 5 pi over 4. And the last one would be? Right?
7 pi over 4.
7 pi over 4. And then it would be a 9, an 11, a 13, a 15, 17. Those are the numbers in the numerator. Okay. So that's the table. Now think about your number line. Just focus on the numbers in the numerator. Negative 1, 1, 3, 5, 7. Let's say we had, this is 0. That's negative 1. That's 1. Where would 3 go? If I was numbering that number line. Yeah? 2 over. You have to skip 1. Why do you have to skip 1? Because 1's not next to 3. And then when you get to 5, you have to skip 1 because 5's not next to 3. And then 7. So that's the only thing that's tricky when you set up your numbering. And I probably wouldn't even number 0 because I don't need 0. When you number it with the values in the table, it's the same thing. Negative 1 pi over 4, positive 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So these are the tick marks you're focusing on. You are skipping every other one. Okay? That's the only thing that throws people off a little bit sometimes. But if you get stuck because of all the pi over 4s, just look at the number in the numerator and think how you would number it if it was negative 1, 1, 3, 5, 7. You would have to skip. Okay. And then once you set that up, then the graph is easy. Okay. All right, so that's the horizontal shift. vertical shift. Okay, vertical, it's a lot easier to do because the arithmetic is all going to be with ones and zeros. What kind of operation is involved in a vertical shift? Is that where we do an add and subtract, or is that where we do a multiply? Yeah?
Is that adding and subtracting?
Adding and subtracting. Now, horizontal shift is also adding and subtracting. What's different about vertical? Yeah?
It's something that is on the outside.
It's on the outside, yes. So it's going to be like plus or minus, usually on the end of the function. What you are adding and subtracting is outside of the argument. That's a vertical shift. The only way that it could be a horizontal shift is if you did that. And that's a weird amount to shift by. It's just not common for a horizontal. Okay, even if I did parentheses here, that's still a vertical shift. I mean, it's still a vertical shift. To make it horizontal, the letter and the number have to be grouped together. I mean, even if you add extra parentheses here that are pointless, that doesn't change anything. That's still a vertical shift. With vertical shifts, it's not the opposite. Positive would move it up, negative would move it down. So now we do the same thing. We're going to take our table. One column gets adjusted, one column stays the same. If we're moving up and down, which column is not affected at all? Yeah?
Or X.
The x's. So what's nice about the x's staying the same is you don't have to worry about all the pi's and the fractions. Every vertical shift in the homework tonight will have x values of 0, pi over 2, pi, 3 pi over 2, 2 pi. None of those will change for the vertical shifts. I use D to represent the vertical shift because once we learn all 4 transformations, that is the last one you would do. And you don't do the opposite. If you see a +2, you're going to do a +2. If you see a -5, you're going to do a -5 to all the y values. Let's take a look at that one. Okay, we know it's a shift because it has adding and subtracting is shifting. But how do you know that that one is a vertical shift and not a horizontal shift? Yeah?
No parentheses.
Can you be more specific? Because I could put some parentheses in there and it would still be a vertical shift.
The x and 2 are not in the same set of parentheses.
Right. That 2 is outside the argument. Yeah. All right. So we know that's a vertical shift. So which column is staying the same? Yeah.
The X's are staying the same.
X is just staying the same. And Ben, can you tell me what my x's are?
Would be 0,
Yep.
pi divided by 2,
Yep.
pi,
Perfect.
3 pi divided by 2,
Yep.
and then 2 pi.
2 pi. Now the original y's I'm just going to put off to the side for reference. 1, 0, -1, 0, 1. And what are we going to do to all those y values to get the new ones? Yeah. Just going to add 2. So we're going to get 3, 2, 1, 2, 3. So that I think you'll find the arithmetic a lot easier with the vertical shift. That's it. That's your table. All right. Let's make our sketch. Okay. and label the axes. I'm going to label my axes 0 to 2 pi. If you don't label them, then the assumption is each tick mark is 1. Okay, so you need to put labels. At least on the x-axis. You don't need to on the y unless you want to, because we're going to go by ones. Okay, so we got 0, 3, 2, 1, 2, and 3. And remember, with cosine, you're getting that middle part of the wave, so just make sure it has a curve to it. Like that. So that's a vertical shift. Any question on that one? All right. Any question how you would do a shift down? You just subtract 3 from all the y values, but the x's would be your standard 0, pi over 2 pi, 3 pi over 2, 2 pi. All right. So you know what? Rather than, because I broke it up, we'll do those for the homework. So don't worry about the worksheet. If we had a review day, maybe we would have done that. But those will be the questions that we do for tonight. Okay, so graph and make the table. So for each one of those, you should have a table with 5 points, and then off to the side, you should have a sketch of what it looks like. So those are the 7 questions for homework tonight.